before we get started with our lab. You won't need to do any virtual stuff for this lab. Just what I outline on the board is necessary for the lab. But basically our goal in this lab is to calculate the electric field pattern for a couple of charge distributions that we already hopefully know what they look like when we have a positive and a negative dipole. We know that the electric field should look something like this. And in between the two charges, you're going to have these kind of electric field lines that will circulate around like that. And so our goal then in this lab is to try to reproduce this field pattern and also this field pattern for an infinite plane of charge, which we have, say, positive on this side, negative on that side. It's going to be relatively uniform electric field pattern in the interior, but if the distance d is not small in relationship to L, then we'll get some edge effects. And so I want to look at that and how minimizing those edge effects brings us closer to the semi-infinite approximation that we've been looking at for an infinite plane of charge. But to do that, we need to first talk about what voltage is and how voltage relates to electric field. And so we can define a voltage difference, delta V, and it has to be a difference in order to have the potential to do work. So if you have, for example, a 12-volt battery, it means that there is a voltage difference between the positive terminal and the negative terminal of 12 volts. And so if you just stay at the same voltage, it could be 100,000 volts. And if you had a bird, for example, lands on two wires here, and each one is 100,000 volts, there's no voltage difference. So the bird will be just fine. It's only if one of them is 0 and the other one is 100,000 that the bird is in serious trouble. So we're going to be looking at those concepts today and how they relate to electric field. The guy that got this all going is Volta, and what he noticed is that electric eels were producing a significant discharge of electricity, and the electric eels were using that to kill their prey. And so he analyzed the structure of the electric eel's voltage-producing layers of cells. And he said, well, I wonder if I could do this with regular materials. Like, he started experimenting around, and then finally found zinc and copper had different electronegativities that tended to allow for the flow of electrons. And so basically, Volta was inspired by the electric eel and was able to produce a battery that then could generate electricity. And so to try to tie this in with things that we already have a little bit of an understanding of, let's say that we had a gravitational field and we wanted to move an object from A to B. We could say that the change in potential energy be equal to mg times delta y. If g and delta y are in the same direction, then we would get a negative sign here because you'd have a drop in potential energy if you go from higher potential to lower potential. Okay? But if you went against the gravitational field, then the delta y would be positive because you'd be lifting it up against gravity. You went that way. And so then your angle would be 180, and you would get plus mgy. And so we could define the gravitational potential as being g times delta y. So there's no change in potential energy until a mass moves through that gravitational potential. So a way to think about that is to just think maybe, let's say for example you have a big ladder leading up to the top of the building, and there's no way to fence that off from a playground with a bunch of grade school kids playing around there. Now, even though none of the kids have climbed up the ladder, I know that I'm going to be nervous because I know that there's the potential for disaster. If a kid did go up against that gravitational force, lift its mass up to this height, and then starts throwing frisbees on the top of this thing, we could have disaster where that potential energy turns into some other form. In electrical problems, you have a similar kind of a math situation, and we can actually equate that to what's happening on the surface of the Earth because of lightning strikes. Lightning delivers negative charge to the Earth's surface, and this does vary somewhat, but a typical value during the daytime for the electric field is about 100 newtons per coulomb, where the negative charge is down below and the positive charge is up above in the cloud somewhere, way high up. And so we could think of this as newtons per coulomb, and for this kind of a problem, the units of volts per meter end up being preferable. So the volt is the unit of voltage, and so that's named after Volta, who discovered and built the first battery. That by definition is a joule per coulomb. So that's work per unit charge. Okay? And so we could think of gravitational potential as being a joule per kilogram. We don't usually talk about gravitational potential, at least not in undergraduate classes. But it's the same kind of principle. If you take and you move through a gravitational field, you'd have a change in gravitational potential. If you move through an electric field, you have a change in electric potential. And so it's kind of like if you swim upstream against the flow, you go to a higher state of electric potential. Just like here, when you go from lower to higher against gravity, you go to an increased state of gravitational potential. And so we define this then, if we take the g times delta y and just replace that with E times delta y, we take the mass, we replace it by the charge, then we can think in terms of the electric potential as being a way of giving charges potential energy. So in other words, if you move a charge through a electric potential, then this is associated with a change in energy. When we move a charge through a difference in voltage, this causes a change in energy. So if you had a 12-volt battery, there's no charges flowing yet. And if you allow for a conductor that allows charge to flow, then electrons will flow from the negative side to the positive side, will gain energy. And that energy could be used to light a light bulb or to heat up a heater filament or any of those kinds of things. In just the same way as gravitational potential energy, can turn into kinetic energy or any of the other forms of energy that can take place in a gravitational problem.
This might be a bit of a stupid question, but so in a battery then, is there two compartments where you have one that's heavily negatively charged and one that's deprived of negative charges, and that's what creates the flow?
For our purposes in a physics class, we could just think of it as being a black box, but what is in there typically would be two different kinds of metals with some ion gate that would allow for electrons to pass through, say, zinc and copper is a typical one that would be used. And so in a chemistry class, you would learn about the redox reactions and how electrons could be transferred from one of these kinds of metals to another, because one is more electronegative than the other one is. So after a while then, in order to recharge the battery, you would have to send current through in the opposite direction, and that would regenerate the original conditions that allowed for the voltage to be produced in the first place. So a chemistry class is probably a better place to get all of the details for how it works. Because that's where you deal with the chemical reactions and the redox and all of that stuff. But for our purposes here, it's something, electric eels can do it, and Volta is able to make it happen. And I'll talk a little more about that later too, what his strategy was for actually building that. In a physics class, normally we just kind of think of it as a black box that produces voltage.
Gotcha.
Okay, so if we took something like the Earth's surface and we moved a charge up to a distance of 1 meter, it would gain, well, let's see here, the electric field, E, is equal to 100 volts per meter. Let's just say that's the correct value near the Earth's surface. Now, if we don't have as many lightning storms, or if it's nighttime, or the conditions aren't favorable for lightning, maybe the sun isn't producing quite as much ionizing radiation, which might have something to do with generating lightning storms. Sometimes they've speculated that even supernova explosions that have happened hundreds of years ago, when those high energy particles move through the Earth's atmosphere, can create a conducting path that can enhance lightning strikes. But let's just say on the average that this is a value that we could use for the electric field at a particular point. And because the Earth locally looks pretty flat, we can say that this distance is small in relationship to the distance across the Earth in which this level charge configuration is working. And so if that's the case, then if we go up 1 meter, then the change in voltage is going to be equal to minus 100 volts per meter times 1 meter times the cosine of 180. Because it's a dot product here, E dot delta y. And so since we're going against the field, then the cosine of 180 cancels out the minus sign and gives us plus 100 volts. Okay, and so if we define this here to be 0 volts, and sometimes that's what we do, even though the surface of the Earth may be negative, it doesn't matter that much where we define the ground to be, because it's just the difference in electric potential that we're interested in. And that has an analogy to what we learned before with gravitational problems, where you could define a reference position for 0 gravitational potential energy that is just convenient for the problem that you're dealing with. And so, sometimes they talk about a floating ground and things like that. You can choose it any way you want, but normally we consider the surface of the Earth to be our reference position of 0 volts. And so this line, because it would be the same all the way across, this would be called our 100 volt equipotential line. And this would be analogous then here to our 1 meter topography line. Okay, so this would be an equipotential and gravitational potential energy. You move across here and you don't change your gravitational potential energy. You move across here along an equipotential line, you don't change your voltage. If you go up 2 meters, 100 volts per meter, then up here, this is your 200 volt equipotential line. And etc. We could keep going. This doesn't work this way forever. Eventually, it doesn't increase that fast anymore as we get farther and farther away from the surface. And we start looking at something that isn't really an infinite plane anymore. When we start getting far enough away from it, then we start seeing that there's curvature to the Earth's surface, and the semi-infinite approximation will no longer hold. But at least near the surface of the Earth, we can notice that these equipotential lines are equally spaced because the electric field is uniform in this region of space. We also notice that the equipotential lines always intersect the electric field at a 90-degree angle. So this is a general principle. They always intersect at a 90-degree angle. And so this is also true, though, in any kind of a curved electric field line, too. And so the field lines don't have to be straight. For example, we already know, because I told you, but we're going to show that it's true today, experimentally at least, that for a dipole, we have electric field lines that look something like this. And the way that we justified that those electric field lines look the way that they do was by looking at the electric field from one charge, which will point straight away from positive, but farther away, in this case, from positive, and one that would point straight toward negative, and that would give rise to a resultant electric field that would just be a tangent to the electric field line. And so that's our general utility then of the electric field lines, is that tangent to an E field gives the direction of E. And the spacing, the relative spacing of the lines, is what gives us our magnitude. So we get the magnitude of the electric field from the relative spacing. And so then in close here, where we've got lines that are pretty closely spaced, we know that the electric field is stronger. And out here, where the lines aren't so closely spaced, we know the electric field is weak. So there's a lot of usefulness then to being able to construct electric field lines. But that's a hard thing to do just from basic principles to tell what the electric field is at a certain place. So what we're going to do instead in this lab is generate equipotential lines and then get the electric field from the equipotential lines. And so the way that we're going to do that is with conducting paper. And this conducting paper allows for a very small amount of current to flow through the paper. And so we hook up electrodes to either side, and that is what gives us our electric potential. Okay? And so that gives us an imbalance of electrons between one side and the other. And then what we can do, and so we'll turn this thing on, and then we just adjust the amplitude here until we get 8 volts across these two points here. And we can think of these points here on this thing as being point charges. Okay, and so this is basically conducting paint that is painted right onto the conducting paper. And so then we hook up the voltage here, we have a connection there, and then another connection to the conducting paint. So one thing you don't want to do, because we want the voltage between here and there, and not between here and there. But we can lose voltage anywhere where there's a flaky connection. And we've got flaky connections in this lab. As a matter of fact, you want to be careful that you don't bump this thing as you are taking your measurements. That may change the voltage here, and then cause your whole voltage field to get distorted. So what I would suggest doing is checking often what your voltage difference is from one side to the other. Now to get you used to the concept of measuring voltage, we have voltmeters here. And these voltmeters are digital, meaning that we don't have to worry about figuring out what scale to use. It's much easier to use than an analog meter. But we will introduce you to analog meters when we get to electric circuits. All we need to be able to measure, though, for this lab is voltage. So all you have to do then is move this thing to the volts here, not millivolts, because we're measuring more than millivolts. So just the regular voltage setting, but not the one with the wavy AC line. The one, in this case, it depends on which meter you get. One will have the wavy AC line and a flat DC line. And so it depends on which meter you get, but you can always tell what mode you're in with this little thing. It'll either say DC or AC. If it says AC, then you need to hit this magic little button here, and that'll change it to DC. Okay. I've opened up the lab, and there will also be a pre-lab, but that won't be due until next week, so like next Thursday or something. But you can refer to that for more information about using the meters, and but what I want you to do, just to get used to measuring things, is to measure the voltage of these two batteries, which are sitting there. And so this is just very simple to do. Just you want this thing to be plugged into common here in volts. Okay, it's good to have the red one on the volts and the black one on the common. And then you just come in and touch these things. Okay, and so here, this says 6.38 volts. But if I lost my mind and touched them with the negative to the positive and the positive to the negative, not a problem. It just gives me negative 6.38. So it's foolproof. It's idiot-proof. But with an analog meter, not idiot-proof, that'll try to drive the needle in the wrong direction if you don't hook positive to positive and negative to negative. But with a digital meter, you don't really have to worry. So measure those two voltages. So that's step one. Pretty simple, but it just gets you used to the concept of measuring voltage. Then in step two, what we want to do is hook up the power supply, this is a DC power supply, to the conducting paper which is mounted on this plate. And so you'll hook it up to these little electrodes here. Oops. And then make sure that they are in contact. See, these are sliding contacts here. Make sure it's in good solid contact with the conducting paper. And then one person is going to have a very, very important job in this lab. That's going to be to hold that right there for the whole lab. That's your job. Yeah. But maybe you want to trade up, because that's not the most exciting thing. And so then the other lab partner can touch on this side and then adjust the voltage to 8. Okay, so make sure that you're getting 8 volts across. We can think of these as being point charges, even though it's just little painted things. It is simulating the same kind of electric field that we would get for point charges. So you have something like this then. There'll be positive and negative. The positive will be the plus 8 volts. This will be your 0 volts for ground. And then we want to check this often and adjust if it changes from 8 volts. Why might it change? Well, because there's 2 good reasons. One is that you might bump it. Easy thing to do. You just give it a little bump, that might be enough to change the resistance through these things, and it's no longer 8 volts. But you want to keep it 8 volts all the way through. A second reason might not be your fault, it's just the number of electrical devices that are putting a demand on the system in this room. Could cause the voltage in the room to drop a little. And so then you would need to adjust for that. But just keep it at 8 volts. Then, next, and there are different ways of doing this part. In the past, we have had the class calculate the voltage at every point on this grid, and then draw equipotential lines from that. But that is kind of tedious and maybe useful, but it's easy to get off track and maybe not put the right voltage at the right point, and very time consuming. And so what I'm going to suggest here is that you find your 7-volt potential point. Okay, now I know it's going to be closer to 8, so maybe in here somewhere. And then I measure 7. Remember that we got the voltmeter, and so we got the, actually that's the ground side. The ground side would go down here, the hot side would go there, and this would be saying 8. Okay? So once we do that, we know that it's 8, then you can move this thing to here until it reads 7. Okay? And then if you move down too far, this might be 6.5. Move up too far, that might be 7.5. So you find that 7 volt. And then find the line, continue this, maintaining the 7 volts, and draw that line. And this is going to be a curved line, because we already know the electric field is curved, so that means that the gravitational potential equipotential lines are also going to be curved. And so continue moving the pointer on a curved path to maintain the 7 volts potential. So you never want to move this one from ground. So you start moving this thing along 7, 7, 7, 7, 7. So maybe it looks something like this. So this would be my 7 volt equipotential line. Then continue for 6, 5, 4, 3, 2, and 1. And these may not be perfect, so don't try to make it look perfect. I'm not expecting it to be perfect. And I'd be suspicious if it were perfect. Okay, and so this would be your 6 volt line, maybe something like that. Then maybe this would be your 5 volt line. This would be maybe your 4 volt line. And your 3 volt line will tend to maybe move a little more toward the negative, kind of curve that way. Then the 2 volt and the 1 volt. Don't go behind. Things get messed up if you go behind. Okay, and so now you've got your voltage field. This is a scalar field. It doesn't matter which way I orient the meter, it's still going to be that number of volts. Now, the gradient of a scalar field can be a vector field. And so that's where we get the electric field. And so you can imagine this to kind of be like lines under topography now. Okay, so this might be your low point here. And so then if you go up this way, it's kind of like climbing a mountain. But if you go this way, your slope isn't as steep. And what do we do next? Well, remember that our goal here was to find the electric field pattern. So now we use this general principle that the equipotential lines intersect the electric field lines at a 90-degree angle. So we do that by just drawing lines that intersect our equipotential lines always at a 90-degree angle. So we know it's going to start from positive. It's going to be perpendicular there, perpendicular there, perpendicular there, perpendicular there, perpendicular there. We bring it on in. And so then you should be able to get a dipole field, at least in this vicinity where you've drawn the equipotential lines, that looks like the one that we talked about before. And then, of course, one that goes right through the center like that. Okay, so draw a few of these electric field lines to get the general sense for how this thing should look. And so this is our intro to electric potential. I hope you've been paying close attention because I'm not going to go through this stuff again, although Mark is videotaping. So if you are just been falling asleep, then you might want to go back when I post this thing and go over it, because this is the intro to electric potential. All right, so we'll draw those in, and then in step 6, what I'd like you to do is calculate the electric field at the midpoint. Between the two charges. So how do we do that? Well, here, if we've got delta V is equal to minus E dot Y, we can rewrite this as E average is approximately equal to minus delta V over delta Y. Okay, now that's actually a little more complicated than that. The X and the Y components of electric field are associated with the slope of your equipotential field along any direction. But here, because we're directly between them, we can say that that's a total derivative. We don't have to worry about sideways components. We already know from previous experience that the electric field at the center, E, is equal to E1 plus E2. So that's going to be KQ over L squared times 2. Where L then would be half of the distance between these two charges. So this is our theoretical value for the electric field. But the experimental value we can get by just taking two nearby points that are near the center. So you want to take the closest spaced equipotential lines to do this. And then, say this is the 6-volt line, this is the 5-volt line. And let's say this distance is 1 centimeter. So in this case, this would be a sample calculation. We could write this then as a 6 minus 5 divided by 1 centimeter, or 1 volt per centimeter, times 100 centimeters per meter would give us 100 volts per meter. So that is in the right ballpark for this experiment, that we would get an electric field of about 100 volts per meter. Maybe a little less for the point charge, maybe a little more for the line-line charge. But this is the procedure then. First calculating the equipotential lines, plotting them up, plotting the electric field, and then doing a sample calculation to get the electric field at the midpoint. Are there any questions about that? Okay, then in part 2, so you'll have these things, you can transcribe your information onto these pieces of paper here. For part 2, this second conductor configuration we can think of as being a cross-sectional view of an infinite plane of charge, or at least a plane of charge. Not infinite, because we don't have the correct geometry. If we had a very, very long distance here and a very short distance there, then we could approximate this by an infinite plane of charge. But we don't have that, which means we're going to get edge effects. So we'll take this one out, put this one in, and you may need a different voltage to get this one to go to 8 volts. We used to use 10 volts, but then we found that our power supply didn't supply 10 volts to this conducting paper because of the large resistance. And so now we've got this configuration. So you want to repeat, get this as 8 volts between there and there, and make sure that that stays 8 volts all the way through. And then very carefully plot the equipotential lines for the plane-plane configuration. So here you'll have something that looks like this. One will be positive, one will be negative. This will be at 8 volts. This will be at 0 volts. So then, and don't forget about the edge effects. So you're going to come in like this along the 7-volt line, and then it'll be probably fairly flat in the middle, but it'll start to curve toward the end. This will be your 7, and this may be your 6. 5, 4, 3, 2, 1. Like that. And so plot 1, 2, 3, 4, 5, 6, and 7 equipotential lines. So if this confuses you at all, just think about what would happen if, because these things look a lot like what you would see on a topography map. If you're trying to read a topography map and you see something that's spread out on this side and really tight on that side, then you know, well, I think I'm going to go this way. Unless you're a mountain climber, then you go, no, I want to go that way. Okay, because this is going to be the steep slope, that's going to be the gentle slope. So the gradient of this has to do with how strong the steepness of the curve is. But a more steep curve here is an indication of a stronger electric field. Okay, and so then you'll draw your electric field. Always perpendicular to the equipotential line. So it should look something like that in the middle, but should have some edge effects near the outside. And so this is what you get then with an infinite plane of charge, where the distance between the plates is noticeable. But here, if we had a really long, then most of it would just be your infinite plane of charge, and you'd have these little insignificant fringing fields here on the side. And so that's when you can use the approximation that you're approximately infinite, when L here is much, much greater than D. So that's semi-infinite. But not true here. So we wouldn't use our infinite plane of charge electric field because we'd have a big error here. Okay, and so this would be finite planes. This would be infinite plane. And so just repeat everything that you did before, all the steps exactly the same, but for the line-line charge, and then in the end calculate the electric field in the center. So right in here, you do this again. Point A to point B, this might be, for example, 6 volts, that might be 5 volts. So you'd have 6 minus 5 divided by 1 centimeter for E average. So that would be 100 volts per meter. 1 volt per centimeter, or 100 volts per meter, just like before. Although they won't be exactly that value. You may need to crank this up a little bit to get it to 8 volts. And so adjust power supply to reestablish 8 volts. And then calculate the electric field at the center as before. So that's it. That's all that you need to do, are these steps that I've outlined for you in, on the board. Are there any questions?